In the second part of this presentation, we are going to focus on supervised models and how much do we have a variable of response and interest. So I've mentioned three examples here where uh, a supervised model can be applied, and I've mentioned the different aspects that have to be taken into account whenever we decide to use a supervised model to analyze this data. This applies especially for predictive models when we are interested in identifying if there's a new observation and where we can classify them. So all these examples are based on classification. One of the most common ones would be the one of the spam. Emails have a model that help to identify whenever an email arrives to decide if it's going to be sent to the spam mail or if it's going to be left in our inbox. So that would be one of the cases of supervised models. Another one that's often used is based on images, satellite images, to identify if it's a forest or if it's a crop or if it's an urban area. So there are models that also look for that to classify what's being detected based on certain pixels of the image, try to identify what's there. And one of the most classical ones would be in clients in banks for data engineering. Whenever someone arrives to ask for a loan and they are evaluated to determine if that person has the possibility to pay the loan or not. Once we have these questions, we have to identify the data sets that we need. In the case of the spam mails, we would need mostly many different emails where we've already identified previously which are spam or which aren't spam. So that's the information that we would require. For maps or satellite images, we would require obviously satellite images with a previous classification, with places where we know that there's a forest or there's a crop or any of the other categories that we would like to assess. And for bank clients, and we've got to have the history of the clients that have already received the loan to identify which of them paid on time and which didn't, which defaulted. After that, we have to process that information in order to transform those databases or those data sets into information that can be analyzed. For example, in emails, they have to go through a process to identify if there's um, if there are some words that come up very often or characteristics of the words. For example, if there are many high caps, if they say the word attention, things that might appear very often in emails. Usually these emails are spam. So those are the traits that have to be assessed for this type of case. For satellite images, we have to have the colors spectrum. Based on that, we can have a database that helps for classifying this. And for clients, for banks, we have to identify what's the information of interest that can be associated to the possibility that a client has to be someone that pays on time or not. So in that case, we would be interested in knowing what's their salary, for example, their if they are independent or if they have a job at a company, their age. So there are different characteristics that have to be taken into account, can be associated to that. And after that, the algorithm that's going to be used has to be defined. For the case of emails, the neural networks could be an algorithm where this can be applied. Neural networks have been used for this before. And for satellite images, there are certain there's different research that tells us that support vector machine yields positive results for that. And for the case of default clients, it varies. There's nothing that's perfect globally, but different tools can be used in different banks. J46 would be a good option. This is a classification algorithm. Each one of these methods have associated parameters. So these are things that have to be optimized in the neural networks. These depend on a decay rate and the hidden neurons. And this can be calibrated to see how complicated or simple the model can become. For support vector machine, they have a cost analysis, and J46 have confidence levels. And for the evaluation, we have to be able to measure the performance. How can we differentiate a good from a bad model? So we've got to have criterion for that. It can be precision, accuracy, and concordance. These are some of the indicators that we're going to see afterwards. There are two types of errors that we can fall on whenever we analyze data with this approach for data mining. The first one would be in-sample error, and this is when we use our data set for training, the data that are going to be used to teach the machine to create that function. Then there's an in-sample error in that case, because normally it's very hard for all the input variables can predict the output. So in the end of this process, we're going to have an error as much as we maximize those relationships between in input and outputs. But there's also an out of sample error. This is an error we can fall on when we introduce new data that the model does not know. So that other error is also important to be measured. And it's also known as the generalization error. Let's say that if we want to use our model, we would have to have a good estimation of what's going to be the effectiveness when we show data to the model that they still haven't seen before. So due to this reason, it's important to do a data set partitioning in order to guarantee that we are going to measure the performance in an effective fashion from our model. So this is divided in a training set. Training is going to be the one that we're going to show to the function that we're going to use, to the learning model that we're going to use, so that it can learn the patterns. So for databases that are mid-size, you can use 60% of the total information of observations that are obtained. And a 40% is left for validation. That 40% for validation is never shown to the model until the end. And it can only be used to assess what's the performance of the model with that data that it does not know. And for large databases, we can keep a 60% for training, and this 20% is going to be left for validation to train those parameters of the model. And finally, we're going to leave another 20% set apart for tests. So this 20% is never seen by the model until the end. So these are some of the strategies that can be used. This can be also called cross-validation, and it can also be done with folds. It's called cross-validation k-folds. And what you can do there is divide the set of observations in equal parts. In this example, we have 4 different parts. And this method is mostly used when we're working with small data sets that we cannot obtain completely, but we want to try and use all the information because we have relatively small amount of information. So we divide it in 4 equal parts, and what we do is to generate groups of folds for training and for validation purposes, always leaving one of those folds outside for validation and keeping the other 3 for training. So what we do is that we execute a model with this result, another one with this result, another one with this result, and so on and so forth, and we do a consensus between the 4. If there's more folds, obviously we're going to have more results. So that's another way to do that data set partitioning. And remember that the objective is to try and have an effective measurement of the performance of our model, to know how it's going to behave when we present new data, to determine how effective it's going to be for predicting those values that we are interested in. And there's another problem, especially with these type of models that are non-linear and that are based on machine learning. That we can create models that are extremely complex. If we make them predict data that they've already seen before, they cannot work perfectly. So this is one of those examples. The green is a model that works perfectly good with the training data. So this has a zero rate of errors. All red is being classified as red, and everything that's blue is being classified as blue. But what could happen here? That if I use new data sets and I want to classify them between red and blue, this supermodel is going to probably have a big error because it perfectly adapts to this data. But if I demonstrate, if I show new data, uh, it probably won't be as effective. So sometimes we have to find there's going to be a compromise between simple and complex models. In the black line, there's a higher rate of errors in the training, but if we do a generalization or we input new data, it's going to be a little bit more effective. So it's always important to try and measure this. There are some examples here of overfitting or overparameterization. This is a concept that we use. So we have sub adjustment, how much we adjust the model. So when it's under adjusted or sub adjusted, we get a curve, but we did a regression. So we can see that it hardly reproduces those data. In that case, the error is big. And the training error is very similar to the validation error. And the same thing for clusters. We can also fall into the same problem whenever we do a separation. If we do a linear separation, we're leaving all these points underneath in the same group. When we use the proper model, for example, a non-linear function that's not so complex, non-linear functions that allows us to do a better classification of errors, what we're going to have in that case is a performance like this one. Right here we can see that these are the interactions that the model have whenever they start to learn, and this can be done as many times as necessary. When the model tries to establish or stabilize the error that's being measured based on that information that has been inputted. And that error between training and validation isn't so different. Validation, of course, is going to have a higher rate of errors than training, and it's going to be lower compared to when we are under adjusting. And in the case when we do this over parameterization or overfitting, this is a model that can predict the values for training, and it can perfectly classify between those two sets. But what's going to happen there is that the training is going to have a very low rate of errors because it's being almost perfect, but the validation is going to have a higher rate of errors. So in those cases, it's going to be necessary to try and look for a model that's not so complex, or sometimes this can be solved by getting more data, more information. So we always have to have a balance between complexity and the general information that the model can have as we assess its performance. And how do we measure the effectiveness of the model? This also varies for regression models and for classification models. So based on this, we can identify if what we are proposing has a good quality, and we can compare between different models how effective they are. For the case of regressions, the best performance measure would be the root mean square error, or RMSE. The idea of this indicator is to try and estimate what is the average of all of these differences between each one of the observations, where we have the observed values and these are the estimated values, and This would be the ideal.
The idea would be for all values to be that were observed be equal to the ones that were estimated. That would mean that the model would be working perfectly. But of course, since this is a model based on machine learning, there are always going to be errors. But the idea is to bring that to the minimum. So this is what this does is to allow us to have a quantification of how far away these points are compared to the ideal scenario. So these differences they can be elevated to the square root to have positive or negative differences. They are averaged, and in the end, a root is calculated. So this RMSE has the same measurement unit as the response variable. And the other thing that is another thing that's used here would be the R square, the coefficient of determination. This can be calculated based on the correlation between the observed response variable and the estimated one with our model. And this is a value that goes from 0 to 1, or it can be multiplied by 100. But the idea is that as R square is the closest to 1, the model is going to have a better predictive capacity. For the case of classification models, we can use this matrix that's called the confusion matrix. In this case, I've done one for an example where we want to classify two different categories, if it occurs or not occurs. And this side of the rows, we have what the prediction is suggesting. If this event happens, crossed with reality, with the columns, and that identifies what really happened in the end. So we can see that the diagonal, we only name the cases where there's certainty. In the case of A, the prediction says it occurs and in reality occurs. And here it says that it does not occur and it didn't occur. And out of the diagonals, we have some errors that could happen in the classification model. One of these would be the false positive, when it says that it happened when it didn't happen, or the false negative, when it didn't happen and it actually happened. So the performance measurements for these ones, the most known ones would be accuracy. This will be a quotient between the amount of cases that have been positive on the possible based on the possible cases. This varies from 0 to 1. If it's 1, it means that our performance is a lot more exact. This is one of the most used measures, but sometimes it has the problem that it does not take into consideration the performance that could be obtained if the whole table worked randomly. So for this, there's an indicator that's a little bit more, that has less bias, that's called kappa index rating, that's based on the possibility that the occurrences that happen in each one of these boxes are due to randomness factors compared to a real quality of the model. The kappa index goes from a -1 to 1, and it's better if it's the closest to 1. To identify what are the best values of the kappa index, there are some suggestions. Among them, one states that if we have a kappa index that's below 0.20, it's going to be poor, and it improves as it goes higher. So it would be a good position or a good situation. The kappa index would be from 0.81 and 1. Once we've taken into account the performance measures that we're going to use to assess our model, it's important to choose the model that we're going to use. This is a small list of the models that we're going to see in other presentations, and I brought it from this link that you can see in the slide, where there's an explanation of the carried package that we're going to see afterwards, where we can do data mining. There's also a large list of models that we could implement. And for every specific case, we can either test several models or establish one unique model to do the tests. It's important to note that each one of these models have parameters that are associated to them. These parameters allowed to assess the complexity of the model that we are assessing. For example, for the case of neural networks, the number of networks in the hidden layer or in the testing, and for the random forest, there's the predictors in each one of the partitions, and for the case of card, there's also a CP value. So these parameters have a space of possible values, and what's done here is to do some tests to determine which one's the optimal. This is an example that I brought from a paper where we wanted to assess a neural network to predict the default level. So the higher the level of hidden neurons, the model became more complex. And what we can observe here is that based on 4 neurons on the hidden layer, or even 5 neurons, that improvement in terms of the error for the model that we are assessing did not increase or reduced too much. So in that case, it's better to select a simpler model. For the case of random forest, a point can be identified where there's a compromise between the considered amount of predictors in the tree. So part of the work that we have to carry out whenever we're doing data mining is to identify those optimal parameters that correspond to each one of the models that we are taking into consideration to assess in our data analysis. The models have another interesting characteristic. Despite the fact that we've named them as black boxes, because compared to the statistics, they don't have those theoretical fundaments or foundations or mathematical foundations that are too strong. Many of them are based on computational processes that do optimization. So sometimes it's very hard to interpret the parameters that are in there and how they relate to each one of the variables compared to the input variable to the output variable. So there are two different ways that most of the models have to understand what's happening within that black box. And among these is the importance of the variables. This mainly works for random forest, but there's also a way to estimate the different models, the ones that are different to random forest. And what this allows us to do is to rank the variables that I mentioned during the presentation, to try and identify what are the ones that are helping the most in the explanation of the variation of the response variable. This is one of those case studies that I showed you. You probably already know this slide, but what this allowed us to identify is to know that the variety, the seed rate, and the nitrogen were the variables that explained better the yield of tons per hectare. So this is also interesting when we want to take a decision based on our data, or if we want to discuss what's happening within the models. We can also generate these partial results to assess the relationship, not only the importance of each one of the variables, so the input variables compared to the output variable. Beyond the ranking, we can also identify what are the optimal rates, what's the behavior, if it's growing, it's got a growing trend or a reduction trend. And this can be done with the partial dependencies, and there's a process that allows us to obtain these curves, and this can vary from one method to another. So that's the way to explore it. And what's the best machine learning method? We have random forest, neural networks, Super Machine, J46. There are many different ones that could be used. And generally, what we are looking for is to try to do a balance between everything that we need. We have a model that we can interpret on one side, and on the other side, that's not so complex, that doesn't have so many variables, that is as accurate as possible. That if we are going to use it to predict something, it should have a good predictive rate, a good performance. We also don't want to spend weeks training a model just to have a small improvement. So the fastest the model learns and the fastest it can give us a result or generate information to help me take decisions is going to be better. It's also important that it has to be scalable. The more data I feed into it, for the applications that I want to use it, I should be able to use it without any inconveniences. So that's part of the balance that we have to do. The key points of the presentation: we know that data mining offers a wide range of tools to exploit the information that we have and to help us take decisions. We also know that you have to follow a very careful process to select the model, to optimize the parameters, to do the pre-processing of the information, and also assess the results based on the importance of the variables and the partial dependencies. But we have these tools that help us to know what's happening with our data. And besides that, we also talked about how to choose a machine learning method and what are the characteristics that we have to take into account to define if it's better than the other. So we talked about interpretation, complexity, effectiveness, the speed, and scalability. Having said this, we finished this module for data mining. I hope that you are able to take advantage of it and see you on the practical part in R.